The challenge that I'll be showcasing in this video comes from our Capture the Flag site, ctf.blockharbor.io. As it sits midway through a sequence of UDS tasks, we expect that you would have already learned some lessons that you need to get started with Security Access Level 3. To avoid spoiling the earlier challenges in the same category, we'll need to gloss over some of the first steps of this one, but stick with us because there's still lots to learn. From the previous challenges, we've learned that unlocking Security Access Level 1 is a prerequisite to reading memory on this particular ECU. To avoid spoiling the Security Access Level 1 flag, we'll reuse the code we wrote to do this unlock, and then we can begin to read the application memory. The clue for the Security Access Level 3 challenge in the User Space Diagnostics category hints that the application might be located at the default application load address, and those of you familiar with the linker or seasoned GDB users will probably already know the address, but if you don't, a quick Google search should do the trick, but for the more tenacious among you, brute force is always an option. When you have the ECU unlocked with Security Access Level 1, which you would know how to do from the previous challenges, and you also think you have the load address, let's try to read 4 bytes just to see if we get anything. So when we attempt reading our bytes at this address, we get the response from 7E8 of 047F 454C 46. And this is a really good sign, because not only did we get a positive response and the data requested, but at the end of the data we returned, we see that 7F454C46, and files typically contain certain byte values which serve as identifiers, and those values tell the application what type of file it's dealing with. For instance, this PNG of NyanCat is displayed by your computer as an image, but if you open the file instead with a text editor, you'll see that the first few bytes of the file read as PNG. These identifiers at the beginning of the file are known as magic bytes, and the bytes that we've spotted in the response from the ECU align with the start of an ELF application file. So knowing this is the start of an ELF, it seems we've uncovered the base address of an application potentially responsible for managing security access. Our next step? Reading the remaining memory. Since we know the starting address of the application, let's read what we can and write it to a file so we can analyze it later and we don't have to do it all in real time in the terminal. We'll do this by extending our script that unlocks Security Access Level 1 to iterate memory addresses, which you would have had to write to solve the first challenges. Our initial step is defining the starting memory address, which we'll assign to the variable A. Next, we establish a handle for the file where we'll store the application code we're about to read. Now, we'll create a loop, concurrently displaying our current address. In each iteration, we want to read memory using the address format specifier we found before. Variable A is our address, and opting for a rather large size, in this case, hex 800. Lastly, we want to document the response we received from the read memory request, recording the data into the file we've previously created. When we run this script, it'll begin to read out memory and save it directly onto the disk. Currently, as I'm making this video, the feature to download files for your Harbor Bay container is still under development, but in the meantime, file transfer protocols such as SCP or services like transfer.sh serve as viable alternatives to get files from Harbor Bay onto your local computer. Now that you've dumped the application memory and you have it on your personal computer, let's begin the process of reverse engineering the application. To start, you'll need to install Ghidra, which is a suite of reverse engineering tools developed by the NSA, and luckily for us, it's completely free because we all paid for it. You can grab the latest version using the link provided in the description below. When you launch Ghidra for the first time, you'll need to create a new project. Opt for the non-shared project option from the menu, and then specify your save location. Once you import the ELF file into Ghidra, the software should automatically detect the architecture. You should expect this to be x86, little endian, 64-bit. And after a brief analysis period of about a minute, we can review the application code that we got from the ECU. The primary objective of using Ghidra for this is to identify exactly where in the code the security access key is validated, and by finding that, we can gain insight into how the correct key is computed. So there's a number of strategies you can use to tackle the issue, and in this instance, we'll kick off by searching scalars, which are values for an instruction like move register x35. The reason we're using this is because this specific instruction represents a negative response code, which means invalid key. So it's a handy shortcut for locating security access since you can filter for the move instructions. And this NRC isn't used by other services, only security access. So we should expect to only find things in the application that are relevant to the security access unlock process. On first look, the results from the search are pretty promising. If you've already done the security access level 1 challenge, this should immediately jump out at you. But if it doesn't, I'll just point it out. And you can see that we found the security access level 1 handler. And right below the search result, we see the handler for level 3. Right now it's pretty messy and frankly it's just difficult to read. So we're going to tidy it up by renaming and retyping some of these values to get something that looks a little bit more like code you'd be familiar with. The listing should be displayed on your screen by default, but if it's not, we'll click here at the top of the page to display the listing on the left side of the screen. And then we'll begin by naming the function itself. At the very top of the decompiled code, click Undefined Function, and you'll see that function highlighted over in the listing. Click in the listing and press F to identify that section of code as a function, and click on the name in the listing, press L to edit the label. For the moment, until we figured out what this function is entirely responsible for, we can just name it to UDS. Going back to the code, let's look at the initial if and see what it's checking for. Presuming that this if is checking for level 1 and level 3, we can safely assume that bvar1 here is checking for a subfunction value for level 1, followed by an else case checking for level 3, which means that the following section of code that spans between lines 120 through lines 127 is the key generation code that will take the seed and create the key. You can see that the following lines are comparing two values and sending a hex 35 invalid key response if there are any mismatches. Recalling that the level 1 calculation is a XOR operation by hex 20202020, we can infer that the data stored at 4F07A0 is the generated seed, local 24 represents the generated key, and local 28 is the submitted key. And by renaming these variables, we can get much cleaner disassembly. So click the variables that we just mentioned and press L to add a custom label for each of them so you can easily see what they all represent. Now that we know for sure that this section of the function is responsible for handling security access level 3, our next move is to clarify the key and seed calculation for better readability. Now, unfortunately for us, when we double click here or try to interact with any of the unnamed values, we get an error at the bottom that tells us the address is not found in the memory we pulled from the ECU. To fix that, we have to tell Ghidra that the memory address does exist and to disregard the fact that the address wasn't included in the initial memory dump. So to do that, just copy the address you wish to define, then click on the Display Memory Map button at the top. Add a new memory block and paste the copied address into the starting address field. Remember to erase the DAT prefix from the address and assign a name of your choice. It doesn't really matter what it is. And set the length to a minimum of 4, considering that we observe addresses ending in A0 through A3, which is 4 bytes. Then when you're finished, click OK, and go back to the decompiled view to click on the memory address again, and you'll see that the error message has disappeared. Instead, we have a memory region that we defined displayed in the left in the listing. Now that we have that error out of the way, we can tell Ghidra that this value is part of an array of bytes. And in the listing, we need to right-click the first value in the array, navigate to data, and create an array that's 4 bytes long. And you'll see that this adjustment is reflected in the decompiled view. You can see here the logic that derives the key from the seed. Now that we can see what the ECU is doing to calculate the correct key, we need to implement the same logic ourselves in order to get the flag. And while this video has guided you through the majority of the challenge, we still want to leave some aspects for you to figure out independently, so you can solve the challenge on your own terms. At vsec.blockharbor.io, go to Harbor Bay and try implementing this decompiled code to create an identical key calculation algorithm. And when it's ready, try unlocking the ECU with Security Access Level 3 to retrieve the flag. Good luck!